So we're making this video in class talking about integrals and summation. Okay, so first let's review what we have talked about so far about finding the sums of the areas under the curve, right? That's what an integral is asking you to do, is to find the area under the curve, and we're doing that by finding or adding up Riemann sums. And there were 4 different ways to do it. So here I'm just going to make a random curly graph, right, just for fun. I'm going to try to make them all look the same. And we'll talk about the 4 different methods that we have used so far. Okay, so if we want the area under the curve from a certain interval, right, this is our interval from A to B, there were 4 different ways that we've talked about so far. One was the left-hand rectangular method. So first we have to break this into, right, so many sub-intervals. And usually the problem that you're dealing with tells you how many sub-intervals that you want to divide it into, right? Or depending on the table that you're given, you can only use certain values from the table. Okay, so we divide our interval into sub-intervals, and then we make rectangles. So here we're using the left point as the rectangular spot, and we're making rectangles, and the area under the curve would be adding up all 4 of these rectangular areas. Okay, and it might be a semi-decent looking area, or it might be absolutely terrible, right? The estimation, these are estimates. So that was the left-hand method, or we could use the right-hand method, right? We're still going to break this into 4 intervals just to be even. So then we used the right side of our graph, and we made our rectangles using the right endpoint. Okay, and we had ourselves another estimation of the area using right rectangles. Okay, and then we talked about a midpoint method, right, with the same interval, using the same number of subdivisions. But now we have to use the midpoint. So you go up using the midpoint, and that's where we're going to draw our rectangle from. Okay, so this is the midpoint rectangles. We use the middle of each of our intervals, our sub-intervals, in order to make our rectangles. Okay, and this one, out of the rectangle methods, this one looks like it gives you the best estimation, because we have some part of the rectangle that is above the graph and some part of the rectangle that's below the graph. Okay, so this midpoint method is a pretty decent way of approximating it with rectangles. Okay, and lastly, we talked about the trapezoid method. So with our trapezoid method, we make trapezoids, of course. So we come and we make a trapezoid where we have the 2 bases of our trapezoid are your 2 different y values. Okay, and this was a pretty decent way of estimating also, because the trapezoid is pretty close to the curve. Now, I've only broken this into 4 subdivisions, but you can imagine if I broke it into even more subdivisions, okay, the approximation would become better. Okay, using the right hand, or maybe this is like halves, right? So I'm halving it all over again. So the more rectangles that you make, the better the approximation of your area under the curve is going to be. Okay, so we can even make more. So I'm going to half all these again. Okay, when we half it, so we're creating more and more subdivisions and making more and more rectangles and getting better and better approximations. Okay, the more rectangles we make, the better the approximations, of course, because our areas, our rectangles, get closer and closer and closer to something that looks like a curve. Okay, so hopefully you remember from somewhere that this symbol is a mathematical symbol that's telling you to add up everything. Okay, this is the Greek letter sigma, and in mathematics that stands for a summation. Okay, and that's exactly what we're doing here, is we are adding up all of these rectangles. Okay, how many rectangles we're adding up depends on how small of sub-intervals we take. Okay, so we are going to be adding up rectangles. So let's see what that looks like if we add up rectangles. Okay, a rectangle has two parts. It has a length part and it has a width part. Okay, so we're going to start with one rectangle. So we're going to have I values of 1. So our lengths, well, we'll see about that. And we're going to go to I don't know how many rectangles, right? We're going to go to infinitely many rectangles. So what we're going to do is we're going to take the limits as n approaches infinity of all of these summations. Okay, so from 1 rectangle to 2 rectangles to 4 rectangles to 40 rectangles to 400 rectangles to 4,000 and 4 million rectangles, right? The more rectangles we make, the better the approximation of our area is going to be. So we're going to start at 1 and we're going to end up with infinity eventually. So let's talk about the width of our rectangles. Okay, up here, the width of our rectangles. How do we calculate the width of this rectangle? That's the question. Okay, so what we do is we have the whole entire interval, right? So we have the interval from A to B, right? That is the length of the interval that we're talking about. Maybe it's 10 units long. Maybe it's 20 units long, right? Maybe it's 4, that interval. And we're going to divide it into I don't know how many sections, right? Here it was 4 sections to begin with. And then I made 8 sections. And then I made 16 sections. So we kept on making more and more sections, and our approximation got better and better and better. Okay, so the width of your rectangle is dependent upon how many subdivisions you make. Okay, usually in the problem, they tell you how many subdivisions that you're going to make. But your width is b minus a divided by how many subdivisions. Right? The length of your interval, that's b minus a, divided by how many subdivisions do we want. That tells you your width. Okay, when we began, that was 1, right? We had a length of 4, and we divided it into 4 subintervals, so we had a length of 1, or a width of 1, and the math was really easy. Okay, so then how do we decide what the length is, right? What is the height, in other words, of our rectangles? What is this value? Okay, if you're given a table, it's just the y value from the table. Okay, so this length is a y value. It either comes from a table or it could come from your function. Okay, and since half of the time we're going to be given a function, that's exactly what we're dealing with, is the function. Okay, the y value or the height comes from the function. Okay, so that's basically what we're doing, is we're going to take each of our equations, okay, we're going to be given a function, and we're going to write it as a summation. Okay, in fact, there's a little extra thing, so that all of the summations don't look the same, we have to have a starting point. Okay, we have to have a starting point. What is our left endpoint for our graph? Because then that determines the first y value so that we have different areas. Okay, so let's look at some examples. Now, hold on to your socks while we do this, because it is not an easy thing to do. It's some pretty major rearranging of furniture, but it's basically just rearranging furniture. So let's start with this one, the integral from 1 to 5 of 2x plus 9. Okay, we want to write this as the limit of Riemann sums. So we start with the limit of our summation. So we always write lim as n approaches infinity of our symbol, our sigma, from I equals 1 rectangle to n rectangles. Okay, this is always how we start. And now we use our formula to finish everything else off. Okay, so our function is 2x plus 9. Okay, so there's one variable in here, and that's x. Okay, so we're going to replace x with this fancy thing here, a plus delta x. Okay, so we have a 2 times, what is our a value, or the lower end point of our integral? it was 1, right? This is our A down here, 1, and this is our B up here. So that's 1 plus. Your delta x is this part. It's the how wide is our window. How wide are each of these rectangles? Okay, so B minus A. The B value was 5 minus 1. Sorry, 5 minus 1 over n. Right? N is going to always be there. And that is times I. Because that's telling us how many rectangles we're going to have of this particular width. And then we're going to multiply that by 5 minus 1 over n. Okay, so with a little bit of simplifying, we can be done with our limit of summations, okay, the limit of Riemann sums. So the limit of our fancy notation of 2 times 1 plus, well, 5 minus 1 is just 4. We'll just do 4i over n, so we'll put the I up in the numerator. It could also go after the fraction if you wanted to put it there. You might also see it after the fraction, times 4 over n. Okay, and that is the sum, so that we're done. So all we have to do is take our interval and write it as a limit of summations. Okay, now what this means is the first one, right, when I is 1 and n is 1, right, or maybe we're going to have one rectangle with a very poor approximation. And then we're going to have a 2, so these are both going to change to 2's. We're going to have 2 rectangles with a little bit smaller and get a better approximation. And of course, the more rectangles we add up, the better the approximation is going to become. Okay, let's look at another example. The integral from -1 to 3 of, well, let's just do 2x plus 9 again. So we have the limit of our sum, the lim as n approaches infinity, of one rectangle to an infinite amount of rectangles. Okay, and we're just replacing our x value with our fancy little a plus delta x. Okay, so in this case, our a value is -1. Plus, let's see, that's 3 minus -1, right? How far is it from -1 to 3? That's once again 4 units, so 4i over n. And then once again, 3 minus -1 is 4 over n. That is the width of our rectangle, and we're basically done. There's nothing else you need to do. Okay, let's do another example. How about the integral from 2 to 4 of x squared plus 9 dx? Okay, so we start with lim as n approaches infinity of our sigma notation from n equals, sorry, not n, but I. Let me erase that. It needs to be I, not n. This is where your I value goes. Of something squared plus 9. Okay, and I'm going to put that in brackets. Something squared plus 9. Okay, so we have to include your a value. So we have an a value of 2 plus the distance from 4 to 2. So delta x is 4 minus 2 over n, which is just 2i over n. Okay, so the I goes inside with your X stuff, and we're going to square that. Okay, that tells us what the height of our rectangle is. And then we're going to multiply it by 2 over n, which is the width of all of our rectangles. We're taking our total interval of 2 units, and we're dividing it into smaller and smaller sections. Okay? Maybe not too bad. I don't think that's too bad. So let's see if we can go the opposite direction. Okay, what if I gave you a limit of summations? Can you write it as an integral? So let's see if we can figure this out.
Wait, you mentioned at the very bottom about the answer books. I should remind your chat.
Sorry about this. One of my excellent students just brought this to my attention. So if we had a formula of x squared plus 9, then we should have that entire formula in here, right? So this is your x part, and then there's the plus 9. So I have forgotten to do that in each of these problems beforehand. Okay, so our entire thing was 2x plus 9. So in each of these, we need to make sure to add that plus 9 in here before you multiply it by your width. Okay? And I did that on both of these. How dare I? Me siento mucho. The entire function is your length. And the outside part is your width. Okay, plus 9, sorry about that. The entire function, whatever your function is, right, there's a plus 9 here in my original function. So I should have had a plus 9 in all of these other things. Sorry. Okay, so now we're here, back to here. This is your summation. So we need to write it as an integral. Okay, some things that we know. Our interval is 2 units long. Okay, you have a width of 2 units for your whole entire interval. So the question is, at what number does your interval start? Okay, so to find that, you look for the thing in front of your I term. And in here, we don't see a term there, right? There's no number in front of our 2i over n, which means your initial value is 0. Okay, if there's not a plus number in front of your delta x, then we start at 0, which means we have to end at 2 because our interval has to be 2 units long. Okay? Now, this part is your x value, right? Our x's, that's our width of our rectangle. So that just becomes an x plus 9, and then we have our integral of differentiation, our dx there at the end. Okay, so this specific limit of sums would be the integral from 0 to 2 of 2x plus 9. Okay, so you can do it from an integral to a limit of summations, or you can do it from a limit of summations to an integral. Okay, simply by rearranging the furniture and knowing what parts go where and what to look for. Okay, so just become familiar with it. I know it's not an easy thing to do, and there's not a whole lot of math involved. You just have to recognize the summation if you're given an integral, or recognize the integral if you're given a summation.